Howdy. My name's Garand Tyson, and I work on protocol here at the Stellar Development Foundation. And today I'd like to talk to you about state archival, the Stellar Network's novel solution to the state bloat problem. So today, I'll first begin by giving a brief introduction as to what state archival is and the fundamental issues we're solving with this protocol. Then I'll talk about some of the security considerations and how that influenced the overall design. Then I'll conclude by giving some insight into the decentralization guarantees that this protocol maintains, as well as what you can expect as the actual user and developer experience. So first, before I get into the actual design, what is state archival and how did we get here? Well, the fundamental reason as to why we're actually implementing this thing is due to Mudang. Now, so for those of you who are not familiar, Mudang is a baby pygmy hippo recently born in Thailand that has taken the hearts and the minds of the internet by storm. To put it simply, Mudang is this year's hottest meme. But I'd be lying to say if we were actually here because of Mudang. It's rather Mudang coin that brings us here today. For those of you who have worked in Web3 for a while, I'm sure you're familiar with the law of Web3, which is that for every meme, at least 1,000 meme coins follow. So here we are. So the fundamental issue with Mudang is what we call state bloat. So the issue with state bloat is that on a public blockchain, such as Stellar, or other blockchains or public blockchains you might be familiar with, like Ethereum or Solana, anyone can submit a transaction. And these transactions can write permanent data to the blockchain. You might imagine that a transaction mints an NFT. When this NFT is minted, every single validator on the network must store the NFT locally in its database. Now, the issue is, whenever you submit a transaction, you pay fees for this storage. However, you have a one-time storage fee. The issue is, once this NFT is minted on the network and maintained, there's actually a reoccurring cost to keeping that state live on the network. You can think of it like a Web2 corollary such as Dropbox. For your Dropbox subscription, you don't pay a one-time fee to have a terabyte of cloud storage forever. This isn't because Dropbox is greedy, but there's lots of cost associated with maintaining databases. But blockchain doesn't work with this reoccurring fee. You pay a one-time fee, and you have a reoccurring cost. Now, the fundamental issue with this is that what you end up with is a system where memes, NFTs, and forgotten tokens slow down the network for everyone. Now, you might have heard, or you might think that we can just avoid this issue by caching, but caching is actually fundamentally ineffective in a blockchain context. The reason being that unlike Web 2, in a blockchain, all state needs to be hashed in a special structure called a Merkle tree, or in the case of Stellar, a bucket list. The issue with these Merkleized hashes is that they require arbitrary reads for all state. Essentially, the way the Merkle trees work, if you write a new entry, say I do a transfer of USDC, that transfer might have to read and rewrite an arbitrary amount of state. And so in our example, suppose I have an NFT from 2015. Even if I have a trade that's just swapping USDC for XLM, if the hash of that USDC entry happens to be similar to the hash of this old NFT, I still have to reread and rewrite that NFT, even if my transaction didn't touch it. So in this way, blockchain databases are fundamentally inefficient, and no data can be prioritized. What this means is that in your blockchain, your USDC and your actual assets that are being actively used are only as fast as your slowest meme coin, even if that meme coin isn't actively being used. And so the fundamental solution to this is what we call state archival. Now, at its core, state archival just changes the way we charge fees. Now, in classical blockchains, you have a one-time storage fee that has a reoccurring database cost on the network. And so what state archival does is it just reconciles that fee. Now we have a reoccurring cost called rent that now matches this reoccurring fee that now matches this reoccurring cost to the network. And so how this works in practice is that every piece of state on the blockchain has to pay a small reoccurring rent fee to stay live on the network. Now, if this fee ever goes to zero, the entry is considered archived. And archived entries cannot be accessed by any transactions. If your transaction has an archived entry in the footprint, it automatically fails. Now, these archived entries are eventually evicted and actually deleted from validators. This frees up these precious resources and allowing us to optimize and prioritize information that's actually being used and actually paying rent. But don't worry. Even if your entry has been archived and deleted from the validators, it can always be securely and safely added back to the live state via the restore operation. Now, for those of you who are Stellar smart contract developers, none of this information is new. We actually launched all of this with Protocol 20 when Soroban hit mainnet earlier this year. And so the rent concept archival, and restoration has been going on since Soroban launched. However, even though today entries are marked as archived and require restoration, we're not actually doing the eviction step yet. Even if an entry is archived, it still lives in the database and isn't actually deleted. That is until Protocol 23. So as Nico mentioned earlier today, starting with Protocol 23, we're actually going to begin evicting and deleting this state from validators. And so today, I'll be talking about the design and how we do this in a safe, decentralized, and secure manner. So if you were here last year, I gave a talk about state archival where I talked about the interface and kind of the user experience story and how it works for smart contract developers. And so that's not really in the scope of today's conversation. All that to say, if you are a smart contract developer, the information that follows probably isn't super relevant to you, but if you're interested in learning how this stuff actually works underneath the hood, here we go. Now the design is a little complicated and there's lots of moving parts, and so I think what makes the most sense is that we're going to start with just a problem we ran into. We're going to solve that problem, and of course, once we solve one problem, another one will come up, and slowly over time, we will end up with the final solution. So at its core, what state archival does is we're going to delete state from the validator and store it off-chain in some other database. Now, whenever you restore an entry, what you're going to do is you're going to retrieve that information from the off-chain database, attach it to the restore operation, and then give that restore operation to the validators. The validators will then take whatever data is in that restore operation and add it back to the live ledger state. Now, the issue is, how do we make sure that this off-chain state is actually valid? See, unlike on-chain state, there is no consensus that's happening once the entry's been evicted. And so there's nothing preventing a malicious user from lying about what their entry actually is. For example, you could imagine that someone has a 10 USDC balance that is archived, deleted from the validators, and add to the off-chain state. They could then lie and attach a 20 USDC balance to the restore operation, and if the validators actually added this back to the ledger, they've now been able to double spend USDC, and this is essentially stolen funds. And so what we're going to do is instead of just storing evicted entries in a random database, all evicted entries are going to be stored in a special structure called a Merkle trie off-chain. Then, instead of just providing the raw data, in order to restore an entry, you're going to have to include both the entry and what's called a Merkle-style proof of inclusion. And so the restore op will require both the entry itself and these proofs to make sure you're not lying. To demonstrate this, let me walk through what a Merkle tree is and how these proofs of inclusion actually work. So here on the left, I'm going to have my Merkle tree. How a Merkle tree works is I have all this data that are my leaf nodes at the bottom of the tree. In this case, our data is our archived entries. You can imagine I have some XLM, of course, our Mudang coin, some EuroC, and then 10 USDC. Now the Merkle tree, starting at the bottom, these leaf values, will then recursively hash these entries. So I'm going to take the hash of first my XLM and my Mudang and get this O cross AE value, and do the same thing for EuroC and USDC. Now the key feature of Merkle trees is I'm going to then recursively take the hash of a hash. And so I'm going to now, to create the root of the tree, hash these two values and get what we call our Merkle root of O cross D8. And so by having this recursive hash structure, just the single hash at the root of the node implicitly encodes all the information below it without actually having to restore it. And what we call a Merkle-style proof of inclusion is just a path from the root node to the entry being proven. So for instance, say I want to restore my 10 USDC value, that proof of inclusion is just the path from the root to that node and all of its neighbors, which looks like this. And what this allows the validator to do is starting at your 10 USDC value, you can then walk up the proof, rehash all the entries on the way up, and then compare both the root of the proof to the root that is saved at the validator and see if you have resolution. So this works as follows. So here I'm going to have all of my archived entries that are off-chain, unprotected by consensus, but stored in this Merkle trie structure. And here I'm going to have my validator. Now the validator only stores live state. It doesn't store any of this archive state. However, it does persist just the Merkle root. This is okay to do because the Merkle root is just a single small hash value, so it's essentially no memory and no overhead in the database. So suppose I want to restore my 10 USDC, so I'm going to submit a restore op with this Merkle-style proof of inclusion. What will happen is that the validator will then start at that 10 USDC node and take its hash. It will then calculate its hash to be O cross 90. Then it will recursively hash those two values and then generate the root of the proof. Now, after it's generated the root of the proof, it will compare this value to the root value it's stored locally, and it sees in this case they match. Now, because the two hashes match, the validator has then proven that 10 USDC actually does exist in the archive, even though it doesn't store that value locally. Now, to provide a counterexample, let's do the same walkthrough, but this time we have a malicious user that's actually lying and saying, oh, and then after the proof is validated, of course, we add this entry back to the live state. But if we were to lie and say instead of 10 USDC, our attacker has 20 USDC. Now, the attacker's not stupid, and so what they're going to do is in their proof, they're going to change all the hashes to match this new value. And so instead of O cross 90, that parent hash changes, and then, of course, it's recursive, so the root hash must also change. Now, upon receiving this restore operation, the validator then goes through the same proving operations, taking the hash, the 20 USDC balance, and then recursively taking those hashes. However, when it gets to the root, the validator notices that this O cross 42 value does not match the stored root hash locally. So in this way, the validator is able to reject this and not add 20 USDC to the ledger because it has been able to prove that this value is not actually correct, and this value does not actually live in the archive state. So that's our first problem we've solved. The problem is that our validators need to verify off-chain data, and we accomplish that by storing this off-chain data in a Merkle trie and requiring proofs to restore it. However, this introduces a new problem. How do validators actually know what the Merkle root is? The issue is, in my example, I was kind of hand-wavy. We magically had this archive, and the validator somehow was able to figure out what the root was. But this is actually a little bit more complicated in practice. So to demonstrate this, you would think that a naive approach would just to have one large Merkle tree off-chain that stores all of your state. And this is what we have here. We have, again, our root node, and then we have this archive state. Now suppose some time passes, an entry runs out of rent and is eventually evicted and archived. So the validator is going to delete that entry and send it off-chain. Now the issue is, when the off-chain nodes adds this to the Merkle trie, it's going to need to change all the hashes. So because this node was added, you need to change your O cross 12 value, which in turn changes your root node. Now the issue is, because the validator doesn't store the entire Merkle trie, the validator has no way of knowing what this new hash is. And so now we have this issue where the saved hash locally in the validator does not match the hash in the archive, and so the validator cannot properly check any proofs like we had before. And so the fundamental issue is that to add an entry to a Merkle trie is necessary to store the entire Merkle trie in memory. And so if we just had one Merkle trie, the validator would be required to store all the archive state, and that completely defeats the point of state archival in the first place. So what we're going to do is instead of having one Merkle trie that stores all the archive, we're going to shard this into a series of multiple immutable subtries. Now, how this will work in practice is that at all times, the validators will locally store what we call the hot archive. The hot archive is just a Merkle tree of the most recently evicted states. So whenever an entry initially is archived, instead of deleting it and sending it off-chain, the validator will first add it locally to this hot archive. Eventually, the hot archive will become full. Now, when the hot archive becomes full, the validator maintains just the root of that hot archive, deletes the rest of the state, and sends it off-chain. This process will then repeat recursively until we eventually have our full state. Let me demonstrate this with an example. So here, let's imagine that we just turned on state archival. So we don't yet have any archived entries, and our off-chain archive trie is completely empty. So some time passes, and our live state will eventually become archived and run out of rent. And so here, we now have our yellow entry that is archived. Now, instead of immediately deleting it and sending it off-chain, we're instead going to save it to our local hot archive. And the hot archive is, of course, itself a Merkle tree, so we're going to compute our root node here. Now some more time passes, and we have another entry that runs out of rent and becomes archived. And so again, we're going to add that entry to our hot archive Merkle tree and recompute the root hash. At this point, our hot archive is full, so what the validator is going to do is it's going to persist just that root node, delete the rest of the tree, and send it off-chain. So that's going to look like this. Our validator just has the root node, and then our off-chain entry has the entire tree, including the entries itself. This process will then repeat multiple times, which means that we'll have multiple Merkle roots and multiple trees off-chain. So in this way, validators are able to know what the Merkle root hashes are in a trustless and decentralized way, because the Merkle or the validators at no point need to trust the off-chain data source to tell it whatever the new hash is. And so the issue of how do validators actually maintain these Merkle roots is solved by sharding Merkle trees into multiple immutable subtries in the fashion I showed before. Now the issue is we now have another vulnerability that these multiple Merkle trees have exposed, and that's what I call the double restore attack. And so to demonstrate this, let me give you an example. So in the double restore attack, first I'm going to have an active USDC balance that's currently live on the ledger, and this, say 10 USDC, and this will eventually be archived. And so, like I mentioned before, we have multiple archival tries, and so this 10 USDC balance is going to be included in my first archive try 0. Now the attacker will restore the entry, and so this entry will be added back to the live state. But remember, these tries are immutable. So even though our 10 USDC balance has been restored, we cannot delete it from this try. If we were to delete it, the validators would have no way of knowing what the new root is, so it's going to leave this try as it is. So then the attacker will spend some of the balance, say 5 USDC, and they will let this new balance of 5 USDC become archived. And so whenever this 5 USDC balance gets archived, it's going to get added to the next archival try, which is archival try 1. And so here we have a precarious situation. There are essentially two different versions of the same balance in the archive. First, we have the up-to-date balance that has the true balance of 5 USDC, but we also have this out-of-date version of 10 USDC that still exists in the archive. And so what our attacker is going to do is instead of getting the proof of inclusion from the correct archive try 1, it's going to submit a proof from the out-of-date older archive. And so the attacker is going to restore the 10 USDC balance. Now again, the validator just maintains the Merkle roots. They don't know what actually data is in these trees. And so all the validator is going to see is it's going to see this proof of inclusion from archive try 0 and say, oh, that checks out, 10 USDC is legitimate. And at this point, the attacker has now restored 10 USDC to the live state, even though they really only have 5 USDC, and has now double spent. And so in order to prevent this double spend attack, or the double restore attack, as I've coined it, what we're going to do is additionally require a proof of non-existence. And so similarly to how I showed you, a Merkle tree can provide a proof of existence. Similarly, Merkle tries can provide proofs of non-existence. Essentially, it's the exact same thing. To prove an entry exists, you provide the path from the root node to the value. To prove an entry doesn't exist, you provide a path from the root to where the entry would exist if it actually existed. This is why we use Merkle tries and not Merkle trees. So what we're going to do is the validators will store the series of roots, but they're going to store them in the order that they've created. So this will be a numbered vector. We'll have root 0, root 1, etc. And so whenever I restore an entry, I need to first include a proof of inclusion for that entry in the archive that exists. So we're going to have a proof of existence in archive try in. Then, for every newer try, I will have to provide a proof of non-existence. What this essentially does is that I am proving that this entry exists in the archive and that no newer version of that entry exists. Thus, I'm preventing the double restore attack. And so, with this new requirement in mind, the requirement of proofs of non-existence, let's examine what our attacker can do now. And so, just like before, we have a valid proof of existence for our outdated 10 USDC value in try 0. But we also have a valid proof of existence in try 1. However, there does not exist a proof of non-existence for try 1 because the value actually does exist. What this means is if the attacker was to submit that outdated proof in the restore operation, the validator would say, okay, try 0, this is a legitimate proof, but where's your proof of non-existence for try 1? And the attacker would not be able to generate it because, of course, there actually does exist a value in that try. And so we've been able to prevent the double spend by requiring these proofs of non-existence. And so we have the issue of double restore, which is defeated by requiring both proofs of inclusion and proofs of exclusion or a proof of non-existence. Now there's one final security concern I want to talk about, and then our design will be complete. And that's what I call the double create attack. And so I'm going to give you another example. So suppose we just turned on state archival such that the archive is empty and we only have live state. Now I'm going to have a victim who's going to mint an NFT. This NFT will then be added to the live state as follows. And this is a NFT at a deterministic address. You can imagine that the address of the NFT is just like the hash of the image. Now eventually this entry will run out of rent, at which point it becomes archived. And so just like I've said before, the entry will be deleted from the live state, add off-chain to try 0, and of course, our validator maintains try 0's root hash. But now what I'm going to do is an attacker is going to recreate the NFT. Now, what a well-intentioned user would do is say, hey, this NFT is in the archive, and so instead of creating a new one, I'm just going to go and restore it. But the attacker notices that the validator has no idea of knowing if the NFT exists or not. So it's going to recreate the NFT at the exact same address. However, the attacker has swapped the owner. And so instead of the rightful owner, the archived version owning the NFT, the live ledger state now has that exact same NFT with a different owner, which is represented by NFT start here. And so essentially, by not restoring the entry, instead of just simply recreating it, the attacker has stolen this NFT from the archive. And now this is very bad, because if the victim tried to restore their legitimate version of the NFT, it would not be allowed because the validator would think that a newer version of that entry exists. So the only issue is that the newer version is now owned by the attacker. And so to solve this problem, we're going to have one final requirement, and that is that all creations additionally require a proof of non-existence. So if you are creating a key for the first time, say if I am a new user who's initializing my USDC balance, that transaction will require a proof of non-existence from every single archival try, proving that that entry is actually new and that doesn't exist anywhere else in the archive. And so this is our final design. In this way, we have a safe and secure way of ensuring that there is no double restores, there is no creation attack, and that every entry being restored is secure. Now, even though this is a correct implementation, it kind of sucks right now because proof of non-existence are super expensive. First off, they're big and take a lot of space in the transaction, but additionally, they're really expensive to create. As you can imagine that, Stellar's been around for over a decade worth of archival tries requires a lot of seeks to generate these proofs. And so entry creation is just way too expensive to be usable here. So what we're going to do is we're actually going to optimize away proofs of non-existence such that they're almost never required. So a proof of non-existence really is just showing that the validator that a given key doesn't exist in some archive. So all the validator needs to know is the set of keys that exist in the archive. Now, a naive solution would just be, okay, we store a set. The validator will delete all the ledger entries, but the validator will maintain the set of ledger keys. The issue is this set is just way too big, and it defeats a lot of the space savings of state archival. And so instead of using classical sets, what we're going to use is a special type of probabilistic set called the binary fuse filter. The binary fuse filter is essentially just an optimized version of a Bloom filter. So this is a probabilistic set, which means it will occasionally return a false positive, but will never return a false negative. What this means is that if a key exists in the given try, occasionally my binary fuse filter will lie and say, oh, this key actually exists in the archive when the key in fact doesn't exist. However, it will never return a false negative. This means that if a key really does exist in the archive, the filter will never lie and say it doesn't exist. So what this means is that all of our safety guarantees are still there. You will never be able to double create or double restore with this false positive, but occasionally you might not be able to create a key that really doesn't exist because the filter returns a false positive. And if a false positive occurs, what the user can do is essentially actually go and create that real proof of non-existence, attach it to the transaction, and this proof of non-existence will essentially override the Bloom filter miss, or the binary fuse filter miss, rather. And the reason we're using binary fuse filters is that they're super, super efficient. So if every single key currently live on the Stellar network was to become archived, the entire filter would only be 200 megabytes. And so even though we do have to persistently store this filter on the validator database, it's very lightweight. Additionally, the false positive chance of the binary fuse filter that we're using is approximately 1 in 4 billion. That means that on the entire history of the Stellar network to date, there's only a 1% chance that even a single entry creation would have required a proof of non-existence. So what this means is that we're essentially able to completely remove the proofs of non-existent requirement by using this probabilistic structure, and we have essentially zero storage overhead by doing so. And so here's our final design. What we're going to do is all of our archive state will be stored in a series of immutable Merkle tries stored off-chain. Then the restore operation will require a proof of existence proving that the entry exists, as well as a series of proofs of non-existence proving that no newer version of that entry exists in the archive. Additionally, when you create an entry for the first time, you have to provide a series of proofs of non-existence showing that that entry actually is new and doesn't exist anywhere else in the archive. But don't worry, we are going to optimize away the proofs of non-existence using this probabilistic binary fuse structure such that we have efficiency. And so I'd like to close by answering a couple of common questions and myths we get when we first talk about state archival. First, will evicting entries affect the blockchain immutability? And the answer is no. Eviction is part of consensus, which means that every validator agrees when an entry needs to be evicted and what entry needs to be evicted. And all of our restorations are backed by proofs, so immutability is always preserved. Next, Who stores the archived entries? Is it safe? Is it decentralized? And the answer is yes. While I didn't talk about this much in this presentation, this off-chain database is actually just the history archives. And history archives are already a fundamental part of the Stellar network and are freely and openly available and maintained by every single Tier 1 network. What this means is that the decentralization and redundancy guarantees of state archival are the exact same safety and redundancy guarantees you get today with a Tier 1 network. Finally, can my data be lost? And can I, essentially, these proofs prove the data is correct, but can I essentially lose the data such that I'm not able to generate these proofs? And the answer is no. Like I mentioned before, every Tier 1 validator maintains this information, and additionally, RPC nodes have a local cache for proof protection purposes. So there's lots of copies of this data. It's very secure, very redundant. Now I'll close by the user experience. Now first, there's a lot of complexity with the proofs here. So when submitting a transaction, how do I know I get the right proofs? It's the exact same as today. Today, you pre-flight with RPC, and it will give you that restore preamble. It's exactly the same in this world, just the restore preamble includes a couple proof structures. So essentially, the entire proof process is abstracted away from you guys. Second, how can I query archive state? The story is similar. Both RPC and Captive Core will provide endpoints that allow you to query both live state and archive state. This means if you're a wallet provider and you don't want to freak a user out by saying that their $1 million USDC balance suddenly vanished, you can just query the archive state and show the exact same value just as archived. Finally, what will you actually notice when this thing gets launched in Protocol 23? Well, first off, storage-related fees are going to decrease a lot. This means lower write fees, lower minimum rent balances, and lower rent cost. This just prevents a lot of DOS, and so we're able to essentially throw those savings back to you guys. Secondly, read-write limits can increase for the same reasons. The only negative is that occasionally restores will be a little bit more expensive because transactions are getting a little bigger in some cases when you have to attach those proofs. Right. I know that was a lot. Do we have time for questions, or do we need to move on? Sorry, I know I went a little over time.